Hello everyone. So this is eighth week of the course transport phenomena for non-Newtonian fluids, and in this particular week mostly we are dealing with so let me just present my screen so that things become visible to you. Just wait. So I'm using second screen for the PDF or something, whatever is needed in order to explain things. Yes, so So, like lecture 25, 26, and 27 of the eighth week, we were discussing about this free convection between two vertical plates, and then this viscous heat generation, and then temperature distribution in fluid confined between coaxial cylinders. So this one, free convection between two plates, we have taken the Cartesian coordinate, the standard Cartesian coordinate, and also for the viscous heat generation, the gap between the two plates. So here we have taken the cylindrical confinement, and the gap between them were like very small, so that the assumption of linear velocity profile we have taken, and then the subsequently we have seen uh, the different aspects of viscous heat generation and how the shearing forces are leading to the temperature distribution within the given annular region, right? And then the temperature distribution in the fluid confined between the coaxial cylinders. So this was the last lecture of the week where you were explained about when you considered the effect of curvature and when the gap between the two uh, the still gap is small, but the gap is not very small that the inner cylinder radii and the outer cylinder radii ratio is very close to one. Rather, it is somewhere in between, right? So so this course, you can see that this transport phenomena of non-Newtonian fluids. So far, we have discussed about how experimentally the non-Newtonian behavior of a fluid is calculated, and based on that, how different constitutive relations for different rheological property and the rheology models, uh, the the relationship between shear stress and shear strain, and are being employed for generalized Newtonian fluid. Most of the cases we have discussed that, and then along with that, sometimes we have seen what may happen with the viscoelastic fluids and viscoplastic fluids as well, right? So this particular class will be we will be solving some questions that will be helping you in solving your weekly assignment, as well as it will be a kind of revision session where we will be revising the things that has been taught in the entire week very quickly. Uh, it's like mini lecture, right? So let's fix it. Yes. So what I'm saying is, if you want to study this particular subject very well, it is very good practice to follow this Bird, Stewart, Lightfoot, and Chabra's R.B. Chabra's book for the rheology of non-Newtonian fluids, along with the course content that are being displayed. Most of the derivations and things are being somewhere borrowed from there, along with some greater depth of explanation that is being provided to you, right? And so first is this free convection between the two vertical plates. We will be revising the contents that we have seen. So let me just project the uh, free convection between two plates slide. So you have seen that the non-isothermal flow of a non-Newtonian fluid uh, is here. Here you are actually describing non-isothermal flow of a non-Newtonian fluid. So what you need in order to describe that, whatever is needed for the Newtonian fluid, that will be needed here also. Along with that, what you need is the equation of energy, right, for the non-isothermal part, and then there could be this thermal equation of state, pressure as a function of rho and T, and then caloric equation of state, equations for density and temperature dependency. If density is depending on temperature or the viscosity, thermal conductivity is depending on temperature, then also that can be considered. And then rheological model of non-Newtonian fluid. Okay, so whatever models that we have seen, the power law model, the Bingham plastic model, the model for this viscoelastic material, and then models for this time dependent fluids, that can be considered. Ali's model, okay, and this Carey-Lucinda model. So those kind of model can be employed in order to uh, look for the particular rheology along with the non-isothermal effects for the particular non-Newtonian fluid, right? So let us come to the next slide. What it says is, uh, so very quick, slowly, we will be looking up the main concepts that was the part of these 20 slides for the 25th lecture of the week 8, right? So these entire set of equation, whatever we have seen, that the continuity equation, the Navier-Stokes equation, or the equation of motion, the energy equation, and then the dependencies of density, thermal conductivity, and viscosity on temperature, and then rheological correlation, the shear stress versus shear strain relationship for the non-Newtonian fluids, those can be incorporated in the given equation. And here equation of motion, what we are using is Cauchy's equation of motion, where we are having everything in terms of shear stress, and those dependencies of non-Newtonian fluids can be used there, right? So prior to obtaining complete, so what you are doing, the entire set of equations solved to get pressure, density, velocity, and the temperature as a function of space and time by numerical simulations. Prior to obtaining complete numerical simulations, restricted solutions may be useful for making order of magnitude analysis or investigating limiting cases, right? This can be done by making some standard assumptions. So first assumptions could be constant physical properties. Second is, which in reality it should not be there, the constant physical property. If temperature is changing, then density, viscosity, interfacial tension, thermal conductivity will change. But here you are deliberately taking them as a constant so as to ease out the calculations that are needed in order to get something out of the physical phenomena that is happening in terms of order of magnitude analysis that you are going to do, right? So these are the investigation in limiting cases, right? So it's these are called asymptotic analysis in this theoretical mathematics. If you see, these are asymptotic analysis, and these are done in order to actually get some insight of the system with some or few mathematical assumptions that are actually taking care of the phenomena, right? Keeping the main essence of the phenomena, right? So second assumption could be zero fluxes. Setting tau and q equals to 0 may be useful in cases like adiabatic uh, flow processes, in which in system designated to minimize frictional effect, where Venturi meter and the turbines, and high speed flows around streamlined objects, right? So one of the assumption that could be there is that, but the one of the dependency that could be incorporated sometime for the density. Most of the time, whenever you see in the fluid mechanics and in advanced fluid mechanics, where you see about this, learn about this hydrodynamic instabilities. What I'm saying is, let me just fix my main screen here so that we can see as well as work on, right? So let us just fix it here. Yes, it is here, and then this. Let me just, okay. So what I'm saying is, yes. So sometimes this let's so this Bosonic approximation, right? So if you see that if you are going to take this temperature as a density or the physical fluid property as a function of temperature, that can be taken in order to actually fix and ease out the mathematical calculation. So that's why in most of the problems that has been solved in the week, you may have seen that this mostly the density as a function of temperature has been taken for this natural convection problem, right? So if you see this Bosenick's equation of motion for forced and free convection, so here this equation of motion has been derived previously, are valid for the isothermal. Okay, so for non-isothermal process you have to rectify it, right? And that rectification is the inclusion of this particular dependency of temperature or dependency of density on temperature, right? So how the classical Navier-Stokes equation that we are having will be changing when you are having this density as a function of temperature that has been explained over here, right? So in non-isothermal flows, if you see, fluid density and the viscosity may depend on temperature, right? And this dependency can be non-linear also, but for the case for the ease of simplicity and to ease out our calculation, like we are here we are solving it theoretically, then the dependency that is taken is this linear, which is the strong dependency of the temperature on the density, right? So and then the third point says that variation in the density is important, and as it gives rise to the Bion force and thus the free convection. So in our problem that we are dealing right now is non-isothermal flows of non-Newtonian fluid, and especially in that we are looking at the free convection between the two vertical plates, right? So that's what is there. So here the beta is what? The expansion coefficient, which is given as minus 1 by rho, del rho by del t, and sometimes this rho can be written in terms of V. So volumetric expansion, right? And T bar is the reference temperature. So if you see that equation 1, which is here, is obtained by applying Taylor series for density as a function of temperature, considering pressure P constant and keeping only first two terms of the series. You are omitting out the non-linear terms, right? So only first two terms when you have considered, you got the expression that is over here. You see this one, rho bar minus rho bar beta bar T minus T bar, right? So if you see this, the equation of motion, that is the Navier-Stokes equation, but the Cauchy's equation of motion, this changes includes this body force term, and here this body force term depends on the temperature, and so the temperature distribution diffusion equation and then this equation of motion gets coupled through this particular term in case of natural convection problem, right? So let me just see. Yes, these are okay. So let me just fix it here. If I can pin it. Okay, so now you have seen this. Yes, if I can fix it. Yes. So the left hand side here, you see this one of the equation of motion, we didn't substituted Bosenick's approximation because it is valid for Bion term only, but not true always. Okay, so here for the time being, in the case of natural convection processes, this the density which is coming with the convective terms are not considered as a function of temperature, but this term becomes important, and here also you have to consider the effect of temperature if you are dealing with sonic speed and high velocity systems with changing temperature. So high velocity, high temperature systems, this rho dV by dt, here rho should be depending on the temperature, then you have to consider this term also as a function of temperature. But for the time being, we are just omitting it out because we are only looking at the natural convection. Here the convection or the high speed is not there. Okay, so An equation 2 describes limiting case of force and the free convection and the reason between these two limiting cases. Okay, so in force convection, the buoyancy term is neglected, right? So this is neglected. In free convection, this delta P and rho g is small, and omitting is usually appropriate for vertical rectilinear flow and flow near submerged object in the large body of fluid. So this 9 minus del P plus rho bar Z equals to 0 means pressure distribution is same as that for the fluid at rest, right? So you can replace this rho on the left hand side by a rho has been successful for free convection at moderate temperature difference. Okay, under these conditions, fluid motion is slow. Acceleration term dv bar by dt is smaller compared to the gravity term in the equation of motion. So dv bar by dt is small as compared to the gravity term in equation of motion. So that's why it can be neglected. For the system where the acceleration is also large with respect to g, which is gravity, one must also use Buzan's approximation for density on the left hand side. That's what I was saying. So hypersonic missiles and then turbine gas turbines, here the left hand side, which is this convective term of the equation of motion, uh, will also depend on the temperature in terms of density as a function of temperature, right? So so let us just fix it here. I just set it, yes. So now what we are doing is, hide this, we are doing is, we are, so I am a bit slow because this particular 20 slides, it will fix up the basis for the next two lectures. Okay, so here you are actually incorporating the effect of temperature, right? Along with the non-Newtonian fluid for the given this free convection problem. And in the next two lectures, similar calculations we are having, but just there we are having some curvature effect and some cylindrical kind of geometry with the non-Newtonian fluid that we will be working on. Then in that, what happens with the viscous dissipation is also leading to the temperature changes, right? So that we will be considering. So this laminar free convection flow between two vertical plate at different temperature that we are looking at. So the diagram that you are looking at is this one. If you see, and we can also have our, so what I can so I can show it here only, but if we can draw it, then it will be better. But okay, so let me just fix it here. Yes. So you can see that this is cool plate, this is hot plate, right? And distance between them is 2b. Okay, this is y direction, right? And then you see here, colder temperature you are taking as T1, hotter temperature you are taking as T2, and any temperature in between is T bar. T bar is what? T1 plus T2 by 2, right? And then this velocity profile for the time being has been considered like this, but it may be something else. It is just that you have to actually find out, right? So a fluid of density Q and the viscosity mu is located between the two vertical plate at a distance 2b distance, right? Temperature of the heated wall is T2 at y equals to minus b, and temperature of the cooled wall is T1 at y equals to plus b, right? Y equals to plus b T1, y equals to minus b is T2. Okay, then assume delta t is very small as the term containing delta t square, delta t cube, that can be neglected. Okay, so this T1 and T2 difference is small, right? So if you see this, we temperature gradient causes fluid near the hot wall to rise and descent near cold wall, right? So if you see that this is hot wall, okay, so I will be explaining it in detail way. So where is the slide? Yes, let's close it. Okay, so suppose this is the plate, right? So let me just see if, okay. So anyway, these recordings will be there, and you can actually go through them as per your wish. And uh, what I'm saying is, these lectures are a bit uh, difficult in terms of calculation, but the physical insights that you will be getting, and how to incorporate the non-Newtonian nature of the fluid uh, with the non-isothermal as well as mass diffusion, that we will be looking at in upcoming lectures, uh, along with the fluid flow, is actually taking the picture of entire things within it, right? So this one is the temperature, right? This is the temperature, that higher temperature T higher, this T lower, right? And the whatever fluid molecule is here the density mu, viscosity mu fluid is there, right? So so whatever fluid molecule is here, they will be getting their temperature raised. Because of that, their density decreases, and when their density decreases, fluid of this region will feel will become lighter, and because of that, buoyancy force will be acting this side, buoyant. And for this reason, the buoyancy force will be acting this side, buoyant at high temperature, buoyant at lower temperature. And that's why there will be circulation of like this. Okay, so that's what I was saying there, and it has been explained. The temperature gradient will cause fluid near hot wall to rise and descend near the colder wall. System is closed at top and bottom. Okay, so from here there is no loss of heat circulating between the plate. Mass rate of the flow of fluid in upward moving stream is same as in the downward, because you are having more or less symmetry problem. So plates are tall enough to avoid end effects. So here end effect is not happening. And then temperature is a function of y alone. Okay, so y is this one. So from here to here y. So whatever del t by del y will be coming up, that will be considered. Anything related to del t by del x or del t by del z, they will be actually omitted out, right? So if you see the equation of non-isothermal system, this is the main equation, right? And now you see that it is a steady state problem, so this becomes zero. Vx is zero. You are not considering v y will be there, but you are not saying that del t by del y exists. You are saying that del t by del y will be there. Okay. So and then this Vz del t by del z. So it is not there. With the z temperature is not changing. The x temperature is not changing. So and Vy you said that Vy you are not having any convexity motion. So Vy is zero. Okay. So overall what you are having from here. Okay. So here you see that del t by del z you are considering, right? How? Vz del t by del z, and from here what you had this del 2t by del y square will exist. Okay, so this one we found. But compared to this term, but convection in the z direction, you are not considering. Okay, is very less as compared to conduction in y direction. Okay, z direction you are having very less convection. This is a direction, right? Here very less convection is happening. So that's why only this term you will consider, and based on that you will have temperature to be del T by del y equals to C1 and then T equals to C1 y plus C2. Using the boundary condition on the B and the minus B T1 and T2, you will get the value of C2 to be T1 plus T2 by 2, and T1 accordingly you will calculate. C2 came out and C1 also came out, right? Then based on that, what you are having is this the temperature profile that you are having. Okay, C1 plus C2. Okay, and T equals to C1 plus C2. Okay, C2 is T bar. Okay, so now this temperature you got, now you can use the equation of motion in Z direction, so upward. So this is Z direction. This is Z direction. In that direction, if you apply the equation of motion, these things we have has been discussed very clearly. And what you will be getting is this for the Z direction velocity, this rho by Z plus this. And for the y component, you will from the y component you will be getting that p is not the function of y, and for the x component you will be getting p is not the function of x. Only this thing you see that for the z component you have this. So now things became easy, right? So what now things became easy? How? You see, delta t is very small here, thus density changes in the system will be small. This suggests that density should be expanded in Taylor series about uh, reference temperature, right? Okay, so density should be expanded in the Taylor series about reference temperature. Okay, so this is the density equals to density bar minus density bar beta bar T minus T bar, right? And also that see where beta is coefficient of the volume expansion at T bar. Okay, and then beta you know. So when you put it here, you will be getting this one. Thus, the equation indicates balance among viscous. Viscous term is here, pressure, gravity, and the buoyancy force. Okay. Now you can use the function of temperature T, whatever you are having. So this temperature function you can use T bar minus 1 by 2 delta T y by B. Okay, in this one. So you are having this function of temperature. When you put it there, uh, okay, then what you are getting, this y by b comes up here. So now this expression you can see that boundary conditions you are having that for the velocity is 0 on both the walls, okay, for y minus b and yb, and then plus b, and then when you solve it again you are going to get two constant which is c1 and c2, and we are again having c1 and c2 constant, but this c1 and c2 is different from what we had here. So it is just dummy constants that we are assuming, and this c1 and c2 can be solved for under the given condition, and you will get the final velocity expression to be like this. Okay, what about the unknown dp by dz? That is another question, because dp by dz is coming here in the velocity profile equation. Okay, for problem statement, net mass flow in the z direction should be 0 as both the top and the bottom surface are closed. So when you apply that, integral minus b to b rho bar vz dz dy equals to 0, then what you are getting is this, you just put it there, and what you will be getting is the entire this term becomes 0, right? Okay, and from here you see that this del p by del z equals to minus rho bar g, that you also know. So based on that, therefore vz will now be only first term. Okay, vz you will be getting only first term. Second term will be omitted out, and average velocity in the upward moving stream will be 1 by b integral minus 0 vz dy. Okay, you solve it and then you will be getting this one. So this is the average velocity in the upward moving stream. This is this vz, which is the average velocity upward moving stream. Okay, and this was the velocity profile, and this is the average velocity profile. So the first question that could be, what is the, let me just frame a question for you. Let me just frame it. Where is this PowerPoint? Okay, so question 1. Which of, let me just, following is correct for the given geometry, right? So what I am saying is which of the following is correct for given geometry, and the geometry is this one, the same geometry that we were talking about. Okay. Okay, so here you are having temperature T1, here you are having temperature T2. This is y direction, this is z direction, this is 0. So your temperature is changing here. Here it is T bar. T bar equals to T1 plus T2 divided by 2. And density is a function of temperature. The rho 0 is rho 0 beta T minus T bar. Okay, so natural convection will be coming up into the picture, right? So question 1A is expression for the temperature distribution. The expression for the Vz velocity distribution. Okay. And C is what? What we are going to look, average upward velocity in the given system. Okay, so as we have seen through our discussion, let me just fix it here. We have just seen through our discussion about the velocity profile and then the temperature profile that we are having. Okay, so what I am saying is this, the temperature profile that you will be getting is T equals to what? T bar, okay, minus 1 by 2 delta T y by b, right? And this is answer 1. Then second is what? The velocity profile that you will be getting is after incorporation of everything, right? What you will be getting? Vz equals to rho bar beta g delta t divided by 12 mu, right? B square, so this is B, this is 2B, this distance is 2B. Okay, B square, this derivation is the lecture 25, right? So it will be very easy for you, you just follow, and now only we had the revision of the same. It is just for your remembering, because you may get direct questions based on these equations, so it is good to have an idea about the same, right? Okay, so and the average velocity, once you integrate it for this minus b to b 0 average velocity, then what you will be getting is rho bar, okay, upward moving string. Okay, so it is average velocity in the given system for upward moving string. Net you will see 0, because both sides there will be up and down. Whatever it goes up, that will come down, so it will be 0. But you have to just give average velocity here. Okay, so V is at average equals to what? Rho bar Z beta bar delta t B square divided by 48 mu, right? So you can get some questions around this. So now moving towards some questions. So let's see this question. Okay, so this question, if you see, yes, things are okay now. Okay, so this question, if you see, for non-isothermal conditions, the variation in the density due to temperature gradient would cause, what will happen? The variation in the density with the temperature we have just discussed. Changes in the velocity profile due to the natural convection, changes in the density with the time, changes in the pressure with the time, and none of the above A, B, C points are true. So which of the following is true? You are just asked this question, you just look at this. Okay, so let me just see this. So we have just seen that the density as a function of temperature led to a creation of velocity profile, because wherever the temperature is high, that particular wall and the fluid element nearby this wall, suppose this is the wall, okay, and fluid element nearby this wall, they will be actually feeling what? The increased temperature of their molecule. So the density of this particular fluid will be decreasing, and in turn these molecules of the fluid will be getting more buoyant forces, and because of this they will be having an upward velocity profile as shown in the figure that we have seen, right? So the option A is correct answer for the given question. So A is correct answer, right? Now the next question is, just look at this. Okay. For non-isothermal flow causing free convection, which of the following approximation is appropriate to incorporate changes in the density due to temperature difference? Okay. Option A is Poisson flow approximation. Option B is Stokes flow approximation. Option C is Buzanix approximation. Option D is none of the above A, B, C, and D. So for non-isothermal flow causing free convection, okay, so for the case of free convection, the temperature difference delta T is not very large. Okay, so this should also be mentioned, but it is understood for the free convection. Delta T means T2 minus T1 should not be large. In that case, you can use this rho equals to rho 0. Okay, now, so what you are you are having, you see this one. Okay, so what you are having is this minus, it gets subtracted, right? So minus what? So let me just have this. I don't know why it is not working. Rho bar beta 2 minus 2. It is correct. Okay, and now here you see that it is called Boussinesq approximation. Okay, so no issues. Okay, so option C is correct answer, right? So now moving to the next problem. So this problem if you look at, let me just fix it here. So this is the option A. Now the option B. Now this is the option C. And option D we are having none of the above, right? So this is option A, option B, option C, and option D. So density variation with respect to temperature can be approximated by Boussinesq approximation, and we have just seen in the last slide option B is the correct answer. So we can see and verify the answer. B is the correct answer. B is correct. Okay. Now coming to the next problem. Okay. So you see that. Consider laminar free convection flow between the two vertical plates. So here you are having this 0.4 centimeter apart from each other. So the value of B you will be getting here at different temperature 30 and 130. Okay. And now uh, properties at average reference temperatures are thermal expansion coefficient is this, and whatever property are there, they're at their average reference temperature. Okay, so that is there. So now this what I'm saying is the thermal expansion coefficient you are having. So let me just write it. The value of beta you are having as okay, and then kinematic viscosity that you are having is, what is the average upward velocity of the fluid, okay, circulating between the two plates due to the natural convection. This is important, right? So let us just do the calculations of a given problem, then we can actually see. Let's save it, and then you will be getting. So this 4 or 5 questions, whatever we have solved, this was around lecture number 125 is the first lecture of the week, right? But it was important because how you are actually incorporating the dependency of the density on the temperature, and which side of the Navier-Stokes equation of motion or Cauchy equation of motion will be modified accordingly, we have seen. So let's clean it. Okay, so if you see this, yes, if you see this, then so the question number 4, if you look at, then what you will be getting is the equation we have already wrote somewhere, but let me just again do it for you. So average velocity in the z direction. So you are having this. This is t1, this is t2, this is t bar. Here you are having distance 2b. Center is this z. Center is z y. Okay, and you are having this density equals to density naught minus density naught beta t minus t bar, and t bar is what? T1 is t2 divided by 2 that we have seen. So when you see that, the average velocity that you are getting is this rho bar g beta bar delta t b square divided by 48, right? And when you put the given values here, so 981 into 10 to the minus into this 10 to the minus is beta, into 100 is the 30 minus 100, the 130 minus 100, into this 0.2. So why 0.2? Because this distance was centimeter, right? Where is by 58. Mu is what? 0.15. So that was kinematic viscosity. Centimeter square by 2. So that mu, no? So this density got divided. So 9.81. This was G. So 9.81. So for centimeter, this 100 million. And this rho you took here, and you had this mu by rho to be kinematic velocity, which is mu, which is 0.15, right? So once you solve it, you will be getting it 0.545 centimeter per second as the average velocity. So that is the even thing. Let me just fix this internet problem. Let me just fix it. Yes. Yes. Now it's okay. Yes. So things are okay. Yes. So back to the meeting, right? So that is this 0.4 545 5 0 point what came this 0.545 is the answer. Okay, so this option is not there, but the answer is correct. So this option you have to modify. So suppose 0.545. This was the correction in the problem, I think. Okay, limited per second. So option D is correct answer. Okay, D is. So now this fifth, sixth, and seventh problem is there. We will be solving them. So fifth problem, let's read it. Then it will be helpful for you to see what is important in the coming lectures that we will be discussing. So let's read it. The temperature distribution at the tip of a ball, point pen, okay, due to the viscous dissipation is given by this. At the tip of the ball point pen, right? So what is the maximum dissipative temperature difference? Okay, just by warming up the pen due to viscous dissipation. If the clearance between the ball pen and the holding cavity is 5 millimeter minus 5 inches, diameter of the ball pen is 1 mm. Viscosity of the ink is 10 to the power 104 cp. 10 to the power 4 cp. Let me just see if this is correct. So this is power. Okay, this 1 mm no issues. This will be power. And this will also be power, right? Okay, so this particular equation is given. But let's see how you will be solving this. So let me just tell you something about viscous dissipation, because this is here in the problem, and what is the main meaning of this, and why this viscous dissipation will lead to the maximum dissipative temperature difference uh, between the clearance and the holding. Okay, so let's see first the basic of viscous dissipation. What is it? So this was the part of this particular second week, which is second week of the second lecture of the week, which is viscous heat generation. And here if you see that what it is viscous heat generation. We can also call it viscous dissipation or internal heat generation due to viscosity. Is the conversion of mechanical energy, which is because of the motion of the pen that we are having right now. Okay, so let me just fix it here. Just fix it. Right. Okay, so this here the mechanical energy from the fluid motion. Here the ink is moving. So when you are having this pen, the ball of the pen is actually having the friction against the cavity in which it is there, and in that region, the annular region is there, whatever annular region between this cavity interior and then this walls outward, it is actually having this ink. Okay, so this mechanical energy from the fluid motion into thermal energy due to the friction within the fluid itself. So because of the friction between the fluid layers, these layers will be actually leading to this what is viscous dissipation, right? And then internal heat will be generated, which will be anyway leading to the temperature change. So this, when a fluid flow, different layer of the fluid move at different velocity. Okay, so different layer of the fluid, they will be flowing at different velocity, right? So suppose it is v1, u2, u3, u4. So there will be this different, so fluid move at a different velocity. Okay, so viscosity resists the relative motion. So relative motion between these fluid elements will be resisted by the property called viscosity of the fluid, creating an internal friction between the adjacent layers. So the viscosity is leading to the internal friction between the adjacent layer, and this friction converts a part of fluid kinetic energy into the internal energy, which is heat. The process leads to a temperature rise within the fluid if the generated heat is not dissipated quickly. So mathematical representation is what? In the energy equation for fluid flow, the viscous dissipation term appears as this. It is this phi equals to mu 2 del u by del x whole square plus 2 del v by del y whole square plus 2 del w by del z whole square for all the three directions, and then the summation of two squares. Okay, so you can see the unit of it is u is meter, and then x is meter. U is meter per second, x is meter. So here per second is square, and then outside is Pascal second. So Pascal by second comes out, and Pascal is what? Force per unit area, right? So based on that, you can convert Newton per meter square second. Okay. So on unit also you can be asked some questions. So what I'm saying is, let me just see. Yes. So this is the expression for viscous dissipation. So here phi is this viscous heat generated per unit volume. Okay, and then this uh, this uh, mu is dynamic viscosity, UVW is the velocity component in x, y, and z direction, right? Then in simple cases like laminar flow between the two plates, the heat generation per unit volume can be written as this first term. Okay, where dy by d is velocity gradient. So when it matters, so what I'm saying is when this matters. Okay, if you see uh, when this matters, what viscous dissipation. I just want to put question mark. Yes, when this matters. It matters when the high viscosity fluid, oil, polymer, or honey is there, and then this high shear rate is there. So lubrication film, bearing, and extrusion is happening. So high shear rate is there. Like bearings, you see the high velocity fluid is moving in the rotating part, and then it is operating at high temperature. High speed flows where temperature rise affects properties, for example aerospace, for example hypersonics. Okay, so in many everyday water flows, viscous heat generation is negligible, but in polymer processing, microfluidics, or lubrication, it can dominate temperature behavior. Okay, So 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 it can dominate the temperature behaviors. So that's why this particular study is important. uh, so the we will be discussing very thoroughly very important lecture of the week, which was the week 2. Okay, and then we will be moving towards the week 3. So let me just take this particular slides, right? So let's just put it here. Okay, no, I will be just putting it here. So it is here only. Okay, so this viscous heat generation. Very slowly, I will be going towards, and I will be taking up all the important concepts. So far, we have seen what is heat generation because of the viscous shearing between different layers of the fluid, the molecular friction which is there because of the viscosity give rise to the local temperature. The origin of it is molecular motion or the friction, right? So let's see. So viscous heat generation between this coaxial cylinders. Here you are having this coaxial cylinder. Just the gap, about the gap there is these two discussions. So in this particular lecture, whatever gap we will be having, we will not be taking the curvature effect. And in the next lecture, which was the seventh lecture of the course and third lecture of this particular 8th week, there we have seen and we have considered the effect of curvature, and we will be finally looking at the velocity profile and the temperature profile, how the curvature effects got incorporated themselves in the overall flow behavior of the fluid element, right? So consider flow of the incompressible Newtonian fluid between, so here we are considering Newtonian fluid between two axial cylinder where inner radius of the outer cylinder is r, right? So inner radius of the outer cylinder is r. Okay, inner radius of the outer cylinder is r, and then the surface of the inner and the outer cylinders are maintained at temperature T0 and Tb. Outer cylinder moves with the angular velocity omega, where the inner velocity cylinder is stationary. So this is this. You see everything is here. Inner is this, outer is this. Outer is at a distance r. That's why it is moving with the omega. Who is moving? The outer cylinder moves with the angular velocity omega. Inner cylinder remains stationary, so it is 0. Okay. Then T0, TB, inner, outer. T0 is inner, TB is outer. Then because of the friction between the adjacent fluid layer, viscous heat is being generated here. Viscous heat is generated. And in these conditions, viscous force dominates over the pressure force and the velocity profile is linear. So that is important. So viscous force dominates pressure force, okay, and velocity profile becomes linear. So that we will be looking at through the Navier-Stokes equation, how it will be coming up into the picture. And then width of the annulus space between the two cylinder, which is B, is very small compared to the radius of the outer cylinder, so that curvature effect can be ignored, right? So this width B, you are considering it to be very small, so that you are not actually looking at this is when this gap is very small, then the curvature effect of this cylinders can be uh, can be assumed to be not affecting the overall rheology of the material, right? Okay, so that's what we will be looking at. But what I'm saying is, let me just fix it. This particular geometry here, if you see that here, when you zoom it out, very when you are very close and the gap B is very small, you can consider it almost as a flat or parallel plates. Okay, so that's what is considered over here, right? Okay, So now in these conditions, so because the friction between the adjacent layer, so viscous heat is being generated, and in these conditions, okay, this viscous force dominates over the pressure force, and the velocity profile is linear. So right now you are considering linear. Why? Because of this two things. This curvature effects you are not considering, and then this gap is very small, and then you are saying that this viscous effects are very large as compared to the pressure force. So width of the annular space between two cylinder is b, which is very small, and schematically represents the aforementioned problem statement and obtained temperature profile within the annular space between the cylinder. So you have to find the temperature profile within this. This is parabolic they are showing, but it could be anything depending on the rheology of the material or the fluid that is flowing through it, even if there is this viscous dissipation happening, right? So it is very important for you to not to assume it to be parabolic, rather go with the procedure that will be conveyed to you, right? So now the limitations is this vz velocity is only existing, and vz is a function of x, so only vz. So this is x direction, this is z direction. So you see that along the b you are considering x, even it is cylindrical, but this particular region you are taking it to be Cartesian, right? Very slowly I will be discussing this particular lecture because it was a bit tricky in terms of calculations, and then this mostly in the regular UG courses or the regular fluid dynamic courses, this viscous dissipation is not studied well. They are sparsely studied, or just some definitions you are thrown up. But here we are having the entire derivation and how it is coming up or leading to the changes in the velocity profile that we have seen, right? So it is that important right now. So here the Vz velocity is only existing and is only exists, and it is function of x. Temperature is a function of x. Steady state incompressible flow you are considering. So del by del t you are taking to be 0, and density changes you are taking to be 0. So divergence of v equals to 0. Constant physical properties. So no viscosity, density, anything, thermal conductivity, they are not changing with the temperature. Curvature effects here you are not considering. Next lecture we will be considering, right? So that is another aspect that should be there, but when we will be considering that and when it becomes important, that too we will be discussing, right? Cartesian coordinate can be applied now because the curvature effects you are not considering, right? So it is given that the velocity profile is linear. Where it is given? Where it is given? Here only. So here it is giving that because the frictional force is there, there will be heat generation, and the viscous forces are dominant over the inertial forces, so velocity profile is linear. So now it is linear as you consider, so you can assume it to be C1x plus C2, and accordingly, based on the boundary condition that you are having at x equals to 0, Vz equals to 0, and x equals to b, Vz equals to Vb. Okay, and Vb is what? Vb is R into omega. So, so you can get the Vz. So this velocity, this same profile can be obtained by equation of motion as follows. So this equation of motion, when you see del rho by del t del by del x, this, okay. Then the equation of motion in the Cartesian for this you will have this one, okay. And steady state, it is here. Vx not exists, Vy not exists, Vz exists, but Vx by is not existing, so it becomes 0. Del p by del x, we don't know about this. And then here, Vx is 0, okay. Uh, Okay, so these things are not there, and then rho gx body force were not considered. So Vx is 0. This entire thing will be 0. So only this says P is not function of X. Similarly, Py is not the function of X. And then here you will be getting Pz del P by del Z to be this. Why it will be sustained? Because Vz is the function of X1. So it will be existing. So from here, if you see, but in the viscous dissipation situation, pressure force is small. So you will just neglect this term and only this term will be existing. So here you will get linear velocity. So even you are not given that the linear velocity profile is there, you can calculate it using our conservation equations, right? So, so it is that clear. So what is important right now? You are looking at various derivations, some model problems, and you are using the standard equation of motion in Cartesian and the cylindrical coordinate along with the equation of temperature distribution, whatever you have derived for the non-isothermal cases, right? The first non-isothermal cases derivation which was there in the third week or fourth week, that is very important. So you please revisit those derivations. It was a bit lengthy in that sense, but the final expression you can refer to and you can apply. So what is very important is whatever you have studied till now, how you will be applying them in your experiments, right? In your system. For example, maybe you will be doing your research work. So how these concepts that are being taught over here is applicable to your system. That is the overall agenda of this particular course. This is a course designed in order to impart what are the main points that has to be considered if you are considering the non-Newtonian fluid, or you are taking up the advanced fluid dynamical considerations into the system, and starting from the Cauchy's equation of motion. For most of the problem in this particular course, you have seen that we are starting with the Cauchy's equation of motion. That was not true for other fluid dynamic courses that you have or you may have done, right? So let us move to the eighth slide. So here you see that this is the temperature equation. So this we have derived in that particular third or fourth week. Okay, fourth week I think, not third, fourth week. Because first week was the basics, second week was this capillary viscometer, third was this rotational rheometer, and fourth was these fundamental equations that we have derived, right? The continuity equation, Navier-Stokes equation, or the Cauchy's equation of motion, and then these non-isothermal thermal diffusion equations, and those things we have come up with, right? So here in those only mu into phi v, which is this viscous diffusion, viscous dissipation term is there. We are considering that only for the time. And in this particular problem, you have seen that temperature is only the function of x. So only this will be existing and rest will be becoming 0. Steady state, and then dx is 0, vy is 0, vz exists, but del t by del is not the function of z. Okay, so you got it. And this particular thing we have just discussed in the slide that we were discussing about, right? So if I can show you in the slide where we have discussed it. Here, see, we have discussed. Okay, so if you see this, so from here, this mu into phi x, if you see, only this particular first term you are considering up here. That's what we have. I have told you. Vz by Vx will be existing up here, or is first one for this particular case, and then temperature distribution you will be getting it like this. Okay, so this C1 and C2 you have to evaluate. For that you are having boundary condition that at x equals to 0, t is t0 equals to t0, and at at b it is t, right? So accordingly you will have this value of C1 and C2, and when you will putting it here, C2 is T0 and C1 is what? 1 by b Tb minus T0 plus mu by b, mu by k, Vb square by 2. So it came to be like this. Okay, Vb is the upper water pressure. It is a kind of wet kind of situation because it is actually cylinder is like this and outer cylinder is rotating like this, right? So it is another thing. So This is very important. Okay. Yes. C1. Yes. So now the temperature distribution you can easily calculate. So now you got to know about C1 and C2. Just put that back and rearrange the equation. You will be getting this. So once you rearrange this equation in terms of this T minus T0 divided by TB minus T0, this particular factor that is there, this you can consider that is to be Br, and this is called Brinkman number. And you actually have to consider that this Brinkman number came up when you considered it to be Newtonian fluid. Okay, so let me just write it here. Okay, so let's just create one question out of this because it is very important. Okay, so let's consider it here. Okay, okay, so let me just see. My pen is not coming. So I will just fix it. This pen I will be fixing. Okay, okay, so what is the expression or the Brinkman number in case of one is what? Newtonian fluid, rotating between two axial cylinder, inner stationary, outer rotating. And if second is power law fluid, power law fluid. So this thing you have to solve. So the first now we have just derived for is this one. Is this one. If you see this Vr equals to what? Mu Vb square. Vb is this upper velocity. This Vb is what? Omega into r. K Tb minus T0. Okay, so that is here. So this is for Newtonian fluid, right? So let us now discuss this lecture. So I think we can solve now the first question that we were discussing about. Let me just see if I can. Yes. So the first lecture we were discussing about was this. So this question, if you see that, consider viscous heat. I think this will be solved. I think we have already done. Okay, we have solved it. No, we have not solved it. But let us solve it. This one, because this derivation we just did, right? Yes, this derivation we have just done. So let us close it. Yes. So this one, if you see that t minus t0 divided by tb minus t0, and now Brinkman number, and here you can see that what the fluid is rotating, nothing is said about that. Okay, so we will be actually looking at that. So new slide. Let's just omit it out. Okay. Okay, so we will be looking at this. Okay, so let's solve this one. So here this temperature distribution is given. So let's just copy it out. Okay, so at the midpoint x equals to b by 2. At the midpoint. Here it is as at the midpoint. So consider the viscous heat generation between the two axial cylinders maintained at a different temperature and at a distance 0.2 apart. For this case, temperature profile can be obtained as like this. Outer rotating cylinder is at Tb equals to this, inner cylinder is rotating this. What is the temperature? Is 1. So here Brinkman number is 1. Midpoint between the two cylinders is house. So B by 2 is the midpoint because the cylinder was having this distance B, right? So here you are having dB equals to omega into R. Here you are setting this B0. So when you do this, you will be having T minus T0 divided by T minus T0 equals to 1 by 2 plus VR is given 1 by 2, 1 by 20, 1 by 2. So it is 1 by 2, 1 by 2, and 1 by 2. So this is 1 by 2, this is 1 by 2 already, this one, and this is this one, and here 1 minus 1 by 2 is 1 by 2. This is this one. Okay, so this will give you t equals to what? 30 plus 50 minus 50 is given. Okay, 50, this is 30. Okay, and then here you will be having 0.5 plus 1 by 1/6. Here is 1. Why 160? Formula just right? So when you solve it, it's 30. Then 50 minus 30 is what? 20 into what? Wait. Okay. So it is 500 is 500. Okay, something will come like this. Okay, so it will be 42.5. I can tell you nonsense. 42.5 is correct answer. B is correct answer, right? So that's for some little options for this place, but the answer is this one. So you may look at this. Okay. Now, if you see, let me just look at this problem. This one, na? So in this one also, if you see the temperature distribution at the tip of the ball point pen due to the viscous, let me just see if things are okay. Yes, due to the viscous dissipation is given by this T minus T naught 1 by 2 Bp square by K x by B 1 minus x by 1, right? So let's just discuss some more theory and then we will be coming up into the derivation part, right? Sorry, questions, right? So this one we have derived. So now if this viscous heat generation in the coaxial cylinder due to the motion of the power law fluid. Now you are considering a non-Newtonian fluid. Okay, so if the viscous heat generation is in axial cylinder is due to the power law fluid, let me just fix it like this. Okay, so let's just fix it. Yes. Okay, so this one, if you see, yes, this 16 slide is very important. So if the viscous heat energy generation is in coaxial cylinder is due to the power law fluid, then how to get temperature profile? You cannot say that same temperature profile will be applicable here also, but now things will be changing. How the things will be changing, we will be looking at them. So the equation of continuity you will be using, and then equation of motion. So equation of continuity, you will see that it will be anyway followed, right? So it will give zero steady state, and then this del by del x vx, del by del y vy, and del by del z vz. These things will be zero, and you will get that this is satisfied. And then this equation of motion in x direction will give you that pressure is not the function of x position, pressure is not the function of y position, will come out through the equation of motion for the y direction, and then in the z component, right? So if you look at this uh, for through the component, here you see that you are using the Cauchy's equation of motion, right? Why? Because the Cauchy's equation of motion will only be giving us space through which we can actually incorporate the correlations for the non-Newtonian fluid, which is for generalized Newtonian fluid, which gives the power law, right? Okay, so if you look at this, then z component is this one, and through the z component you got to know this. Here also this vz is the function of x, so that's why you see that v at tau fz is existing. Okay, and then the same pressure is very small as compared to viscous forces, because you are actually considering this viscous dissipation effects are large. Then this del tau x by del x will become zero, because this will be very small pressure influences. So now here you just put the equation of motion. Okay, so tau x, you understand it is c1. Now tau x z you are knowing from the equation of motion for this power law fluids, and through this you can evaluate Vz equals to C1 C2 like this. C1 by m minus C1 by m to the power 1 by n x plus C2. Okay, so this is the velocity profile. Under this condition, for x equals to 0, Vz equals to 0, and x equals to v, Vz equals to vb, you will get the velocity profile along with the constants over here. So you get the linear velocity profile here also. So it came out to be linear velocity profile under the assumption that we have made. Okay, we have generalized equation of change for energy. This is the general equation of change for energy. And in this one, if you see that now you are having this non-Newtonian fluid, so is this general, in this general equation of motion, you are not using that phi into new into phi terms, because that was for the Newtonian fluid. For the non-Newtonian, this del into E you have to evaluate, and then V dot Z you have to evaluate. So here E is this one, right? So it is coming from the fourth or fifth week, and then use pi equals to pressure plus shear stress, right? And simplify. So E is this one, right? Okay, so E we need to simplify for us. Okay, so once you do these simplifications, since velocity component in x direction is 0, first term in right hand side will be wave equation is 0. Okay, so x component of q in E expression is minus k dt by dx. Okay, so it's that heat. Yeah. So this is this one in expression of E. This is q will come out with this, and then x component of t dot v is tau x x vx plus tau x y vy and tau x z vz out of different components. So in this one, tau x z vz will be existing, because vy and vx is not there. So only vz will be existing. Why? Because vz is the function of x only, right? So ex you can calculate, only ex will be existing, ey ez will be 0. So ex is what? Q is minus k dt by dx plus vz, this, and this term becomes 0, right? And q, this entire first term becomes 0, because it is the function of what? The velocity. So now this one, if you see, considering steady state and discarding gravity, we will be looking at this, that del E equals to 0 out of this, and then del rho they will become, and these are 0. So Ex is function of C1. Now Ex you have already had, this C1 you can equate. So Ex you had this one, and this is equals to C1. So through this, when you put tau x z here and t you know, and C1 you don't know for the time being, but when you go for temperature distribution you will be getting this one. So velocity was the linear. Now temperature is depending on the m and n, the rheological property of the fluid. And this C1 and C2, if you want to calculate, you are having this x equals to 0, t equals to t0, and x equals to b, t equals to tb. That can be measured through the temperature actuators that can be placed over there. So thermocouples can be used for that in real systems, if you see the problem in that term side. So what you are having is these C1 and C2 can be evaluated, and finally the expression for the temperature you are having this. So now the Brinkman equation for the power law, right? So that was the question that we were asking. So let me just write that. The Brinkman equation for the power law fluid. I think we were writing it here. Here. For the power law fluid, for power law fluid, Brinkman equation is what? mb squared divided by db minus t0 k b by b to the power n plus 1. It is for power law. Okay, so that is the change that came up in the picture. So now this viscous heat generation. So you can see that the temperature profile is depending on the rheological property. So that is the thing that we wanted to calculate. How the non-Newtonian fluid behavior also plays its role in rise in the temperature because of the viscous dissipation, right? That's what is calculated over here. So if let me just fix it. So this viscous heat generation in slit flow is happening. So viscous heat is being generated in a sage flow. So find the temperature profile for the viscous heating problem shown in below. So here you see that VB is similar problem that we have just solved. So x equals to t equals to 0 and x equals to b. You are having qx equals to 0, right? So that's what the assumptions that has been told you to you for incorporating non-isothermal behaviors in the system. What assumptions you will be making. So these are the assumptions that can be made out in order to actually look at the thing. So I think that has to be taken into account, right? This is the last problem that you got to solve. So this is the problem. So these were the assumptions that you made. Steady state encompasses a constant physical property Vx only x Vz equals to Vx, temperature distribution for x, and then accordingly velocity profile got to be linear, and then the energy equation you have employed over here. So here the Newtonian fluid you have considered, I think non-Newtonian fluid you have not considered. That's why you are directly using these expressions for the evaluation of the temperature profile under the given assumptions, and then you got to know that this is the temperature profile T minus T0 divided by mu v square by K x by B this. So about this also we were having some questions. So let us solve that. Right. So I think this question is about that. This question. Let's put some new slides. Let us solve this particular question. So they have related it with the ball pen kind of setup where this friction between the ball pen and the cavity, the temperature distribution at the tip of the ball point pen due to the viscous dissipation is given by this. What is the maximum dissipation temperature difference by warming of the pen due to the viscous dissipation if the clearance between the ball and the holding cavity is this inch, diameter of the ball is 1 mm, viscosity of the ink is 4 cp centipoise, and then speed of writing is 100 inch per minute, and the thermal conductivity of the ink is 5 × 10 minus 4 calorie per second centimeter degree Celsius, right? So let's solve it. So when you solve it and when you actually look at the problem very carefully, this was the fifth problem. We have solved the sixth problem anyway. So after this, we will be solving one more problem. So fifth problem is this one. So then what I'm saying is, let's remove this. Okay, so what is there? So this T minus T0 divided by TB minus T0 equals to 1 by 2 mu VB square. These kind of term also comes for the in the Brinkman equation, Brinkman's expression, right? So we have seen in the last slide TB minus T0, right? X by B 1 minus X by B. Okay, so T minus T0 we have to calculate, it is 1 by 2 mu VB square by K. Okay, X minus X by B 1 minus X by B. How it came up, and everything will be multiplied by what? It will be cancelled out, right? So both side it is there, so it is coming up like this. So same expression we have written. Okay. So now T minus T0 is maximum when is at x equals to xb. So from the geometry we can see that with the midpoint it will be maximum. How? Because you can use this, suppose this is P, so you have to maximize P, so del dP by dx is equals to 0, you just put it 0 and then see the sign of d2p by dx2, and when it is less than 0, right, it means this critical point will give you p max. So x equals to x max, it will give p max, then x max come out to be b by 2, and when you do that, t minus t0 max equals to 1 by 2 mu vb square by 2 by k 1 by 2 1 minus 1 by 2, it will give 1 by 8 mu vb square by k, right? So now once you put it here, that t minus t0 max equals to 1 by 8 mu vb square by k, it will give you 1 by 8, right? Mu v square by 10 to the power 4 into 0.01 gram per centimeter second. 100 into 2.54 given as 60 centimeter per second whole square. 5 into 10 to the power minus 4 into 4.184 into 10 to the power 7, so calculate gram per centimeter divided by second, right? So when you solve it, what you will be getting is t minus t0 max 0.011 Kelvin, right? So the answer to this is 0.011 Kelvin. So answer B is correct answer for the given problem, right? B is correct answer, right? So this part of the lecture is completed, right? Now let us move towards the next lecture, which was the last lecture of the week. and next 15 minutes, so I will be completing this in 10 minutes, and then we will be solving last question of this particular lecture. So this is important because here the curvature effects is considered, but the last week we have not considered curvature effects. So the temperature distribution in the fluid confined between coaxial cylinder, again it is similar to that one, but the temperature distribution in the fluid confined between two cylinders, here the considered an incompressible liquid confined between the two coaxial cylinder. Outer cylinder rotates at, let me just first save it here because it is important. I will be anyway sharing all the slides that is there, the questions and discussions that we are having over here, and then you can actually revise this uh, at your pace. Okay, just save it, right? Okay, so the consider an incompressible liquid confined between the two coaxial cylinders. Outer cylinder rotates at the, okay, let's make it like this. Okay. Outer cylinder rotates at the steady angular velocity of omega naught. Consider the ratio between the radius as lambda, and this lambda is fairly small, but this lambda is not close to 1, so that the radii of inner and the outer is very close, and then we are actually considering that to be this, I mean, same, right? So then the sixth point is inner and the outer surface of annular regions are maintained at the temperature T lambda and T1 temperature. So T lambda is not equal to T. Okay, so one is T1 and then another is T lambda. Right? Inner and outer. So inner is T lambda and outer is T. Okay. So assume study laminar flow and neglect the temperature dependencies on the physical property, obtain the temperature distribution in the confined liquid. So you have to consider. So here the assumptions that you are making is Newtonian compressible fluid, steady, and the laminar flow, constant physical property, and there is no reaction in the system, right? For schematic, from schematic, only V theta exists and it is a function of R, right? So only V theta exists. Now it is not linear, so we have to see how you will manage it. So temperature is a function of R only, and then temperature is a function of both R and Z. Pressure is a function of both R and Z. It is given, and temperature is a function of R only, right? Temperature is a function of R only, and velocity V theta exists. It is a function of R only. So temperature and velocity both are function of R, and pressure is a function of R and Z. R and Z. Z pressure is function of R and Z. Temperature is R only. V theta is function of R, right? So let us see how we will be going. So first the continuity equation we are going to solve for. So from the continuity equation you see that it is a steady state, right? And there is no Vi, there is no Vz, so only V theta term we don't know about. So dV theta by V theta is coming up into the theta. So it is this. Rho can be again because it is considered to be constant. So from here we can see that V theta is not the function of theta. Rather, we have seen that V theta is a function of R, right? So here you can see V theta is a function of R. So R component of equation of motion will be giving you accordingly if you solve it. So V theta is square by R equals to del P by del R, and it will give you theta component will be giving you this one, and then equation of motion will be giving you for Z component will be giving you hydrostatic pressure. Okay. Now from this particular second and third equation that came out of the theta component of equation of motion, you can see that you can derive for this theta, V theta, and V theta comes out to be C1 R by 2. Using this relations that at R equals to lambda R, V theta is 0, and R equals to R, V theta equals to this one. we are having the constants evaluated, and accordingly we will be having our velocity profile v theta. Okay, so v theta comes out to be like this, right? Now you see that this v theta is a function of r omega, right? And then this ratio between the two radii is also coming up in the picture. Okay, so now if you see this v theta by r equals to this, right? Del v theta by del r, v theta by r you have calculated, just rearranging the above equation, and then d by dr v theta by r you are calculating, and you are getting them like this, right? So equation 9 will be utilized in simplifying energy equation. So for the time being, you just keep it here in the energy equation. This time you will be replacing by this. So now the energy equation is this one. For the viscous dissipation, you are having this mu phi v. Here also you are considering the viscous dissipation, and for the viscous dissipation, if you consider, you are always considering the parallel plate or the two concentric cylinder in which one part is moving, another is rest. Sometimes you are having that gap to be very small, and sometimes it is significantly significant when you are going to consider the curvature effects. You cannot consider them to be parallel like a parallel plates moving adjacent to each of them. Okay, so here if you see, based on our let's see why it is coming up. It is there or not? Yes. So if you see this one, yes, so energy equation, when you just rearrange them and then see, then this particular term we have already derived, and we will be putting that here, and when you put it here, then this particular overall picture comes up. So you know that r by r is zeta, you just assume it, and t minus t lambda divided by t1 minus t lambda equals to theta. So these are the scales that you have taken, and now in terms of this, when you do the calculations here, the Brinkman number is coming out to be this, and you see that this Brinkman number is similar. So here it is similar Brinkman number like we have had it there. So now when you solve it and just change that for the given scaling parameters, change the parameters, finally you will be getting this particular expression for the temperature distribution in this particular thing. Here you have considered the effect of curvature, right? So let us just solve the last question that is there, and then we will be revisiting our final derivation, right? So let's see the last question. Yes, so this is the question that we want to solve. So consider the flow of viscous lubricant between the two horizontal. Let's solve it like this. Two horizontal surface. Top surface is moving at a velocity of 500 centimeter per second, right? And then is maintained under constant heat flux, where the bottom surface is stationary and maintained at T0. So let us just 30 degrees Celsius. The temperature profile for this case can be obtained as this, where mu 0 is viscosity of the lubricant and K is the thermal conductivity of the fluid. 4 into 10 to minus 4 calorical centimeter degree Celsius. What is the maximum temperature in degrees Celsius for this confined slit flow geometry, right? Okay, so we will be solving this question, and I will be actually explaining you the steps. So similar question we have already solved, but this one also I will be actually putting each and every step in front of you so that things become easy for you, right? So if you see that here, you are having this, just here you are having this T0 equals to 30 degree Celsius, right? And then here the constant flux at top surface is there, and then what you are having is Vz equals to Vb at x equals to b. Here system is like this, it is slit, x is here, z is here, this is b, v equals to v0, and here v equals to v equals to omega into r, omega naught is this. Okay, so let's see the distribution of temperature, whatever is given over in the problem is this one. Okay, minus 1 by 2, right? So whatever is asked here. Okay, so what is the maximum temperature for this confined slit flow geometry, right? So so that again, you know from the last problem that at midpoint point temperature will be maximum, and it is x equals to b by 2, right? Maximum minimum concept, that whatever we have seen, it is equals to 1 by 2, right? So from here, this t minus t0 divided by mu vb squared by k squared 3 by 8. So t minus t0 3 by 8 mu vb square by k, right? And once you put all the values whatever is given to you, what you will be getting, t equals to t0 plus 3 by 8, right? Here whatever is given, 2 gram per centimeter. Okay, okay, and then whatever is given, 2 mu is what we are having, centimeter second, right? And then it is what, vb square is 500 square centimeter square second square, and then here k is 4 into 10 minus 4. Calorie you have to change, and then centimeter you have to keep, so it will be gram centimeter per second. And once you solve it, you will be getting what, 300 plus 4.8136 into 10 to the power minus 6 into 500 square, right? Once you do that, the value of t equals to 314.203 you will be getting, and it will come out to be 41.23 degrees Celsius. So if you see the option C is correct answer, right? C is correct. Okay, so now Now if you see that the problems that we were discussing, the problems that we were discussing the last lecture, the effect of curvature you have considered, and because of that, if you see that the final expression that is here, the file of temperature that is coming up here, this r is coming up in the picture. This is anyway the location, but the the curvature that is there, that came up into the picture, and that's why the things, if it is the difference, this ratio lambda is not very small but not very small that it is close to 1, then you can actually see this kind of profile which is here. You may get this particular questions based on this particular equation, for which we have not solved in this lecture, but similar problem we have solved. So please go through these lectures carefully. For 3 problems we had 3 different Big Bang numbers, and one was the Cartesian one. Okay, so thank you so much. And now this was the week 8, and we had it very well, and we have solved sufficient problem on this free convection between two vertical plates, viscous heat generation, and then temperature distribution in the fluid confined between the coaxial lines, right? So thank you so much. Thank you.